Mars, the red planet. It's always captured our imagination, hasn't it? This idea of sending people there. It feels like the ultimate frontier.
Absolutely. It's been a dream for generations.
But, is it just a dream? Or is it something we can actually achieve? Because when you think about it, no human has gone beyond low Earth orbit since Apollo ended way back in '72.
That really puts it in perspective, doesn't it? These long-duration, long-distance missions are incredibly difficult.
Exactly. So that's what this deep dive is all about. We've got a stack of sources here, some great stuff from the Planetary Society, the Guardian 2, and we're going to pull out the key insights, the real nuggets about the daunting challenges, but also the surprising breakthroughs in getting humans to Mars.
Yeah. And the goal is to help you get quickly up to speed on this really complex topic.
Right.
And we're looking at, not just the hurdles, but the amazing ingenuity that's popping up. It's fascinating how problems that seemed, almost insurmountable are now being tackled with new tech, sometimes even like accidental discoveries.
Okay, let's unpack that. Starting with maybe the most fundamental challenge, something you just can't engineer away, the sheer distance.
It creates so many problems. Communication is a big one.
Right.
Yeah. Dana Ice from NASA's Mars Campaign Office really highlights this. To the moon, it's pretty much real-time chat.
Instantaneous, almost.
Basically. But Mars, depending on where the planets are, you're talking 4 to 24 minutes, just one way.
24 minutes.
One way. So ask a question, wait for the reply. That's over 40 minutes, minimum.
Wow. That completely changes how a crew operates, how they'd handle an emergency.
Totally different. And then there's this other thing. Solar conjunctions.
Oh, right. This is where it gets really interesting, maybe a bit scary.
Yeah, so every 26 months or so, the sun gets right between Earth and Mars.
Blocks the signal.
Exactly. For about 2 weeks, it creates a communications blackout. Radio signals get distorted, basically useless. Imagine a crisis hitting then. The crew is completely on their own.
That's a huge risk. What's the plan? Just hope nothing goes wrong for 2 weeks.
Well, NASA's not just hoping. They're exploring options. One idea is a relay system, like putting communications satellites elsewhere in the solar system.
To route the signal around the sun.
Potentially, yeah. It could cut that blackout from 2 weeks down to maybe just a few hours.
Okay, that's better.
And there's also laser communications. They're testing that right now on the Psyche mission. It promises way more data, much faster, better signal quality than radio.
So, okay, technically, maybe we can bridge the gap. But what about the people, the human side? Those delays, that isolation. That's got to be tough psychologically.
Oh, absolutely. Research shows it's really difficult. Feelings of isolation, definitely. But it can also impact, thinking clearly, performance under pressure.
Making decisions when help is 40 minutes away.
Precisely. It means astronauts need to be incredibly self-reliant.
Which brings us to another potential showstopper, radiation.
Yeah, that's a big one. A really big one.
What's the core problem out there between here and Mars and on Mars itself?
Okay, so Mars doesn't have a global magnetic field like Earth does, and its atmosphere is super thin, like less than 1% of ours.
So no natural shield.
Exactly. High-energy cosmic rays, particles from the sun, they just shower down onto the surface and through space. That's a serious health risk for humans. Cancer risk, potential cognitive issues, even acute sickness on the journey.
So shields up, but how? You can't just wrap the ship in lead.
Right.
Too heavy.
Right. Traditional shielding is heavy, and launching mass is expensive. People talk about force fields, but the power needed, the materials, that's still firmly in the realm of science fiction for now.
So are we stuck?
Not necessarily. There's this really interesting material being developed, hydrogenated boron nitride nanotubes, BNNTs.
Okay. What's special about those?
Well, they contain carbon and nitrogen, which are good for shielding, but crucially, they also have boron, which is excellent at absorbing secondary neutrons. Those are nasty byproducts of cosmic rays hitting other materials.
And the nanotube part.
That means it's strong, lightweight, and flexible. You could potentially weave it into spacesuit fabric.
Whoa, into the suit itself.
Yeah. And use it as a structural material for the spacecraft, habitats, rovers. It offers protection without the massive weight penalty. It's a potential game changer for how we think about shielding.
That's incredible. Okay, so we've talked about getting there, surviving the trip, but what about staying there? And crucially, getting back. That seems like a whole other mountain to climb.
It absolutely is. And that's where this idea of ISRU comes in situ resource utilization.
Living off the land.
Essentially, yes. Instead of hauling everything you need from Earth, especially something heavy like oxygen, You make it there.
And the big news on that front is MOXC, right? The experiment on the Perseverance rover.
Exactly. MOXE, the Mars Oxygen In Situ Resource Utilization Experiment. It's been a huge success.
Successful.
It managed to pull carbon dioxide from Mars's thin atmosphere and split it into oxygen, producing about 12 grams an hour. That was actually twice what they were aiming for.
Wow. And that oxygen has 2 uses.
Yep. Breathable air for the astronauts, obviously. But maybe even more important, it's the main component by weight of rocket propellant. Oxygen is the oxidizer.
So you make your return fuel on Mars.
That's the goal. Making the oxygen there saves launching tons and tons of it from Earth. Michael Hecht, who led MOXI, says his team is ready to scale it up.
What are the remaining challenges for that?
Well, they need to show a bigger system can run reliably for a long time. And they need to figure out how to efficiently liquefy and store the oxygen produced. Plus, getting water ice seems plentiful under the surface, but mining it, transporting it, that's another logistical puzzle.
Okay, so ISRU is promising for staying and returning. But before you can even think about leaving Mars, you have to land there safely. We hear about the 7 minutes of terror for rovers.
Right, that automated sequence where everything has to go perfectly.
But landing humans with a much, much bigger spacecraft, that sounds exponentially harder.
Oh, it is. Rob Manning at JPL, their chief engineer, calls EDL entry, descent, and landing the single biggest challenge for human missions.
Why is it so much harder?
Scale. We're talking about landing something that weighs 50, maybe 100 metric tons. Perseverance was 1 ton.
50 to 100 times bigger.
Exactly. And you have to slow that massive thing down from tens of thousands of kilometers per hour to a gentle touchdown, all in that incredibly thin Martian atmosphere we talked about.
Which doesn't offer much drag.
Hardly any compared to Earth. So the technologies we've used, parachutes, airbags, even the sky crane that landed Curiosity and Perseverance, they just don't scale up to that size. They've hit their limits.
Okay, that sounds bad. But you said earlier things are improving. The outlook's better than it was, say, a decade ago?
Definitely. There have been a couple of really promising advancements. First, LOFTIDE.
LOFTIDE.
Low Earth Orbit Flight Test of an Inflatable Decelerator. They tested it successfully in 2022. It's basically a huge inflatable heat shield about 6 meters across.
Inflatable.
Yeah, it deploys in space and inflates rapidly. They tested it in Earth's upper atmosphere, which has a similar density to Mars's atmosphere. It creates way more drag, helping to slow the spacecraft down much earlier and higher up, which reduces the intense heating, like a giant air brake.
Okay, that makes sense. What's the second thing?
This one is really interesting, almost an accidental discovery. It's called supersonic retropropulsion, or SRP.
Firing rockets backwards while you're still going supersonic.
Exactly. For years, engineers were worried about that. Would it be unstable? Would it create too much heat and turbulence?
Seems risky.
It did. But then, SpaceX started landing their Falcon 9 boosters.
By firing their engines to slow down for landing.
Right. And people like Rob Manning at JPL watched this happen again and again, and they realized something unexpected. When you fire those retro rockets supersonically, the shockwave actually forms a kind of protective bubble around the vehicle. Yeah, it sort of insulates the spacecraft from some of the buffeting and heating you'd expect. It was new physics, basically, learned from watching reusable rockets come back to Earth.
That's amazing.
Yeah.
An unexpected solution.
It really shifted the thinking. There are still technical challenges to work out, but there's a lot more optimism now that SRP is a viable way to land really heavy payloads on Mars.
So we're seeing these incredible engineering solutions taking shape, really chipping away at these huge problems. But then you hear these really bold predictions about when we'll actually get there.
Yeah, there's definitely a tension there. Elon Musk, for example, back in January 2025, laid out some very ambitious timelines.
What did he say?
Uncrewed starships heading to Mars in 2 years, first crewed flights maybe 4 years after that. And his big vision is a self-sustaining city on Mars in about 20 years.
A city in 20 years. That's fast.
Extremely fast. His reasoning is profound, though. He says, being multiplanetary will vastly increase the probable lifespan of consciousness. You have to give him credit for making Mars feel relevant and urgent again.
No doubt. He's definitely pushed the conversation forward. But what do let's say, the established experts think? People who've spent their careers studying Mars at NASA.
Well, Jim Green, who used to head up NASA's Planetary Science Division, offered his perspective. He called Musk, someone with wonderful attributes, a real space geek.
Right.
But he also said Musk is very unrealistic in his timescales.
Okay. Why the skepticism? Is it just caution, or does Green see obstacles Musk maybe overlooks?
Green puts it in historical context. He reminds us how far we've come.
Ah,
Mariner 4 in 64 sent back those first blurry pictures. Then Viking landed in 76, analyzed the soil, sent back amazing images,
what?
but they landed in what Green called the safest area. He compared it to landing in the Sahara Desert and expecting to find abundant life on Earth.
Fair point.
Then there was a long pause in exploration, some failures in the 90s. But Mars Odyssey in 2001 found hints of subsurface water ice. That discovery completely changed NASA's approach, follow the water.
Right, searching for signs of past or present life.
Exactly. Opportunity rover in 2004 found hematite clear evidence of past water. Then Curiosity, landing in 2012, that was revolutionary. It found carbon, nitrogen, oxygen, phosphorus, sulfur, the key ingredients for life.
Proving Mars could have been habitable.
Must have been, Green says, sometime in its past. All this built the scientific case.
And this leads Green to a pretty bold statement himself, doesn't it?
It does. He says, personally, I think there is life there today.
Wow. Present-day life.
He thinks so. Microbial life, probably hidden in underground water like aquifers. And he believes finding it, confirming extant life, will really require humans to go explore. Robots might not be enough.
That's a powerful argument for sending people.
It is. And Green's even thinking further ahead. His current obsession, he calls it, is the theory of terraforming Mars.
Actually changing the planet.
Yeah, modifying the climate, the atmosphere. The first big step, he thinks, would be to raise the atmosphere pressure from the current 6 millibars up to about 60.
What would that achieve?
At 60 millibars, the boiling point of water is higher, and humans could potentially walk around outside without a full pressure suit, maybe just needing oxygen masks. It would drastically increase mobility, make machines work better.
How would you even do that?
He acknowledges it would require something immense, like a vast magnetic shield positioned between Mars and the sun to stop the solar wind from stripping the atmosphere away again. Huge engineering.
Truly monumental. Okay, so bringing it back to the near term. What's Green's practical take on actually landing humans? Soon. Decades away.
He's quite clear. We're not going to be landing 30, 40, 50 people on Mars anytime soon. He thinks we're getting close to having the knowledge we need, maybe another 8 to 10 years.
What's the biggest immediate blocker, in his view?
Finding the right spot. The exploration zone. This needs to be about a 200-kilometer wide area where you can land repeatedly, mine that crucial water ice, find minerals, maybe even produce medicines eventually, a base camp for potentially hundreds of years.
And we haven't found that yet.
There are still 45 candidate sites. They haven't narrowed it down to the top few. Picking the right place is critical for long-term success. It's not just if we can land, but where makes sense for a sustained presence.
So still work to do before picking the destination. But overall, is he optimistic you'll see it?
He ends on a personal note. He hopes to see humans on Mars in my lifetime, in the next 25 years.
25 years. Still ambitious, but maybe more grounded. So we've really journeyed through some incredible challenges today. Communication lags, radiation threats, making air to breathe, just sticking the landing.
Yeah, it's a huge undertaking.
But the solutions being worked on are just as incredible.
Yep.
Inflatable heat shields, BNNTs, making fuel from Martian air, the unexpected physics from reusable rockets. It shows the ingenuity is there.
It really does. And what strikes me is how it requires this blend, this deep understanding of Mars itself, its past, its environment, combined with absolutely cutting-edge technology.
Which leads to a fascinating question, I think. If the technical problems, one by one, are being solved, or at least solutions are appearing on the horizon.
And the scientific drive, especially the search for life, is so strong.
Then what is the biggest remaining obstacle? Is it just a matter of time and patience? Or is it something bigger like the collective will, the commitment of resources needed for something this massive?
That might be the multi-trillion-dollar question, right?
It might be. We've covered a huge amount in this deep dive. So for you listening, what stands out? What part of this epic journey to Mars captures your imagination or maybe raises the biggest questions for you?
Yeah, what does this make you think about our future out there among the planets? And what should humanity's next great leap into the cosmos actually be?